name is Anna Tuttle. I'm the program manager here at the Institute on Ecosystems, and I work with Bruce Maxwell for the Montana Climate Assessment project that we're on. Before I introduce Bruce, I just want to make sure you guys have an understanding of this web layout in front of you in case you need anything. Right at the bottom, there's a Got Questions box, and you can type in questions for Bruce. We'll save them for the end, and we'll make sure to answer all of them. So feel free to ask your questions, but they won't get addressed until the end. Also, on the right corner in the bottom are technical questions. So we have the wonderful and magical MJ who sort of magically makes things work if they're not working. So if you have questions or something, if you can't hear or see or have any other technical questions, just go ahead and type that in and MJ will get right back to you. And then in between we have a poll, just a true or false question, just to kind of get some thoughts going, and maybe while you're waiting. Next couple minutes, we'll get our last couple people on as participants. And then right above the technical questions, we have some web links that you might find useful about climate in Montana, and as well as the webinar archives of the 2 webinars that were done before this one on climate and water in Montana. And we'll also have archives on 2 different websites, on the IOE website and the continuing education website that you guys can access whenever you want. And next week we'll have our last presentation. So next week will be Ashley Ballantyne from the University of Montana Forestry Department, who's the chapter author for the Climate Assessments Forestry chapter, and he will be presenting next week at the same time. And then we'll be wrapping up this webinar series. So today we have Dr. Bruce Maxwell. Bruce is a professor and researcher at Montana State University in land resources and environmental sciences and plant ecology. He works extensively with agriculturalists across the state. And I'm not going to say a whole bunch about you, Bruce. I'm going to let you take it over from here.
All right. Thanks, Anna. Can everyone hear me? I assume that's true. I'll share my screen here first. Okay. So I'm going to talk about the agricultural sector of the Montana Climate Assessment today, and I want to start by acknowledging my co-authors that did portions of the report, at least, and my main co-author was Becky Weed, who is a rancher but also a writer and has helped tremendously in developing this report. We're at a draft stage at this point, but anyway, we have a few things to share. Anton Beckerman is a agricultural economist, and he's been immensely helpful in pulling some information together. Madison Boone and Megan Mills-Nova are both folks that have been working as interns with One Montana, and they were able to help us in several stages of the project, primarily listening sessions, and I'll talk about that here in a minute. Laura Ippolito is an undergraduate student, one of my advisees that has worked with me and helped work closely with Anton in developing some of the economic impacts aspects of this assessment. Laura Burkle, who is an ecologist and works a lot with pollinators in both natural and agricultural systems. Mary Burrows is extension specialist working in plant diseases, and David Weaver is an entomologist working primarily on wheatstem sawfly in Montana, but also has broad knowledge of agriculture in general in Montana. So go ahead and ask questions if you would like by typing them into the box, and I can try to answer those as they come up. So the thing about agriculture and climate is that climate drives agriculture. That's fairly obvious. It determines what crops and livestock we can grow. We have expansive landscapes that are suitable for different forms of agriculture in Montana, but water and length of growing season limits the amount of productivity. Thus, agriculture in Montana has evolved and is adjusted locally to contend with these constraints. Dealing with climate variability is a fact of life for farmers and ranchers, so it is somewhat hard for them to imagine thinking differently about management relative to climate change. In other words, they just don't, they say, hey, we've always dealt with climate changes and variability, so we don't really need, or how is it any different that this climate change stuff is going to affect us? Well, clearly there's some new climate we're going to be dealing with, and we think there will be some important aspects to think about that way. So it's a little bit of a switch for farmers to start to think that this might be important, and I'll emphasize different aspects of that as I go along here. These farmers have always dealt with uncertainty in the climate. In addition, there are economic and policy constraints that often determine exactly how farmer decisions are made, often trumping the adjustments in management that might come from changing climate. So it's really hard to tease apart what's due to climate and what's due to these other kinds of factors when we look at how farmers make decisions and how they respond to climate currently and then are likely to in the future. Clearly, if climate change increases Montana precipitation and growing season length, we should be in good shape. Those are our primary constraints, is growing season length and water. So if we get more of it, we should be relieving a lot of the problems that we currently might have with agriculture. But it may not be that simple, and hopefully you'll gain that perspective as I go through this. So we started this process with a set of listening sessions. We went to agricultural groups around the state and went to their annual meetings, and groups like the Farmers Union, the Farm Bureau, the Stock Growers Association, et cetera, and had them tell us what they wanted to know about climate and what they thought might be useful to them in terms of dealing with the kinds of climate changes that they might have heard about. So our set of questions to them were pretty straightforward. What climate or climate-related information do Montana land managers need? How do they want that information delivered? Should it be ongoing? Who should do it? And who should pay for it? So the idea is that we're envisioning that surely people, if they want this information, are going to want to continue to get the information. So we're thinking this is in terms of a long-term process, a process by which we would create some sort of an assessment that would be ongoing and continue into the future. So our key stakeholders gave us some information, and so to sort of summarize that, a set of points about that, basically we heard that they want long-term, 6-month ahead, scaled down, global climate model predictions, even though they recognize that there's high uncertainty. This was a bit of a surprise to us because we thought there was going to be some sort of natural distrust in global climate models, and they might not think they're useful, but in fact they do. And one of my favorite quotes from a farmer was that hey, we want to know about this stuff, even though there might be a lot of uncertainty with it. Heck, we don't trust the weatherman, but we watch the news every night to make sure we know what they're predicting, at least for the weather. So I thought that was interesting. They'll take the information and then they'll decide how they want to use it. They want to increase prediction accuracy with on-farm and ranch weather stations linked to a network. So they're all getting very interested in having their own weather station and recognizing that their weather might be different than the weather station even in the nearest town, which could be 50 miles away in Montana. But they all recognize that there's microclimates and that they should know something about that, and they would like to feed that into some sort of common place and be able to access that information and even access other more scaled up information from those sites. So having some sort of a network of could be very useful. Growing season precipitation patterns changes at the farm scale. Again, coming from weather stations and from a network, and they start to get predictions that they can be a little more confident about, at least on a daily basis, and know something about extreme events and impacts on key decisions. Planting, input application, calving and lambing times, those kinds of things would be quite useful to them. Drought predictions and mitigation strategies. Clearly, that's fairly obvious one, and they've dealt with drought in a big way over the past 30 to 50, well, forever in agriculture in Montana, but certainly most of them remember keenly those last droughts. Best adapted crops and forage species for changing climate. They're thinking ahead. How should we adjust if we do get warmer, etc.? Can that support some of the grasses that the states to our south are growing to feed livestock? Can we get more productivity out of our system? Excuse me. Site-specific forage production predictions would be useful to them. Many of the ranchers in particular thought that we should be able to do a better job. They'd like to know about what models might say using projected climates, what kinds of forage production they might get. Similar with crop producers, actually. There was interest in greenhouse gas mitigation. What can they do to help solve the problem? How can they help take CO2 out of the atmosphere? And that's an important aspect of what many thought that they might be able to contribute to. And then we talked about the best format for delivery of a report, and most of them thought that a website is good, although it was interesting, many of them are operating right straight off their cell phones these days. So any information that we might deliver through cell phone apps would be recognized as especially useful. So we thought that was interesting. So that summarizes a few of the key things that we were hearing from our stakeholders. And that affected some of the things and some of the ways that we looked at how do we express what's going on with the climate at this point that's relevant to agriculture. Well, I'll use a few of the tables and graphs that you might have seen in some of the previous webinars, but I want to bring to you how these kinds of things affect agriculture in general, and maybe specifically in the different portions of the state. So in Montana, we divide our regions, climatic regions, according to these 7 different regions, and that are on the map shown below the graph there. And those are exactly the same divisions that we use for agriculture, and that's no accident. Clearly, agriculture is dependent on climate, and so it made sense many years ago when that was established that our agricultural regions would follow those climate regions. So what do we see in the way of patterns? Well, again, as some of the other sector leads have talked about, we're seeing warmer temperatures, and this is projected temperatures now, and using degrees Fahrenheit in this case. And this is projections based on the climate models that, in this case, assume that we have an increasing CO2 level up to 850 parts per million, the 8.5 there, and what is likely to happen mid-century, 2040 to 2069. And so where we're seeing is there's basically increases across the board. Maybe in May, not quite as great as in August, but August really stands out. And actually the central summer there, July, August, September, which tend to be already our warmest months, are going to be especially warm. We'll be increasing temperatures up to 7 to 8 degrees Fahrenheit. So that's pretty significant. The other effect that we see is that we have warmer winters, certainly, and I'll talk extensively about that and what the impact on agriculture might be there. But the other aspect that might be especially important, and particularly we see it in the west and north central, is this warming in April, the March-April temperatures, because what's going to happen there is snowmelt. And snowmelt is already occurring earlier, and we're seeing it being a very rapid pulse of snowmelt. And the fact is that a lot of agriculture can't really make that much use of that snowmelt because it goes right on by. In other words, it goes right on out of the state because we really don't have plants growing to the extent that they can use it at that point in time. So that's a bit of a concern. And what that means is that in the later summer months, when it gets really hot, that August, September, October period, when the water is really crucial to finish off some of our irrigated crops in particular, we see that we just don't have the water. And therefore, species like sugar beets that I show in the lower right-hand corner here are really having, could be really challenged to produce some of those irrigated crops, especially as they might rely on irrigation from our streams that basically rely on that snowpack input late into the summer. So the next aspect of that warming temperature, which by the way we're more confident in than any of the climate effects, is that we're looking at major changes in hot days above 90 degrees. So we're going to deal with very much hotter summers and this continuous days of over 90, when you can see that in places like central Montana, where crops are really most of our wheat is grown, we're seeing tremendous heating in that period. If we have extension of 30 or 40 days above 90, that's a lot. And so how does that specifically affect agriculture? Well, one of the things that we're already seeing is with wheat, spring wheat in particular, it tends to be flowering. These are anthers sticking out that have the pollen in them. It's pollinating at this point in time. And in fact, with that kind of heat, we know pollen tends to dry up quite rapidly before it can actually fertilize the flowers in the adjacent flowers or adjacent plants. It doesn't disperse as well. There's all kinds of problems that get accentuated at this point in time. Plus, just the moisture required for fertilization, there's a whole set of steps that basically determine how well the grain fills in the head. So the plant might be ahead and it might be growing fine because of these warm temperatures as long as there's water. But in fact, that process, that heat at that point in time can really challenge these particular species. This is one of the reasons why there's been more and more interest in moving toward winter wheat, although that's not a simple driver. Climate is not just driving that particular switch either. But anyway, spring wheat is really thought to be challenged in this with these hot, dry days in the middle of the summer. Okay, so a little weather analysis that I did a number of years ago, back in 2007, indicated that already we were seeing heating, and basically each one of these numbers across Montana is a weather station. And some of those weather stations have quite long records, up to 100 years. And so I selected a number of the weather stations that did have those 100-year types, and those are the ones that have a box around them. The red boxes are all ones that indicated that there's a significant increase in temperature been occurring between 1950 and 2007. And prior to that, 1890 to 1949, there was no particular trend in the temperature. The only places where there was exceptions to that was in Hamilton and Big Timber, where it had the blue box or blue around the number. So pretty clear, Montana, no matter where you're at in Montana, is seeing pretty significant increases. That changes by these sites, and so that's important too, because again, agriculture sort of has adjusted to these kinds of changes, and maybe they've been slow enough to where we haven't really noticed, but we think that those kinds of changes, those warming, are going to go exponential in the near future. So changes in monthly average temperature as we see and as we saw in the previous graph, how does that affect some of the other agricultural operations? Well, warmer winters certainly favor a number of things: winter annual plants, winter wheat, but also the one of the primary weeds of winter wheat is cheatgrass. And as we know, cheatgrass is not just restricted to winter wheat, but is a problem on rangelands as well. Winter calving and lambing. Warmer winters can certainly improve the possibility to do more of our calving and lambing in the winter, which has some advantages. Many ranchers went to that anyway. In fact, there's almost been a trend away from that to move that into later parts of the year, or stagger it across the year because of markets and things like that. So, but it could be generally a positive in the livestock production arena. Some crop diseases should certainly increase with those warmer winters. We count on warmer or cold winters in some cases to kill off some of the diseases that are important to crops, and that would be true with some of the animal diseases as well. Just to say a little bit more about cheatgrass, because it's such a ubiquitous species across Montana, and it's become a huge problem throughout the Great Basin to our south. And so we're kind of really keeping an eye on that particular species because it can be such a problem going into the future. So one of the things to think about with cheatgrass is that this graph shows the phenology, or change in plant height, which basically tracks phenology. Phenology being the stages of plant growth as they move from seedlings down here in the beginning of that growth to a period of vegetative growth all the way up to the point where they're starting to go to seed, which you see in the picture here. And then as they start to senesce, often cheatgrass turns purple. Many of you are probably familiar with that at first, and then it dries out. What's interesting is I have a curve here showing basically what it's been in the past, and then the other curve predicting what it's more likely to be into the future, in terms of how that phenology will change. And what we're seeing is an earlier senescence of that species. In terms of the days after emergence, could be even earlier. Cheatgrass, as it is, because it's a winter annual, germinates in the fall and starts to grow in the fall, then grows rapidly in the spring. It's going to seed by mid-June, maybe even early June. And what we're seeing is the senescence is moving all the way up into the last couple weeks of June, whereas it maybe before wasn't until at least mid-July that it was actually senescing. So what does that mean for agricultural producing areas is these black boxes are an indication of the average number of lightning flashes. So natural fires can occur and can ignite these, and this has really been what's especially aggravated the problem in the Great Basin, and we think could also be the case in Montana if climate continues to change the way it is. Because what we see is that through this progression of this phenology to drying out those plants, that they become really susceptible to fire right at this point. And if they weren't fully senesced yet, they wouldn't be quite as susceptible to fire as they are, as they might be into the future. And so we get in this process of seeing a lot of fires in this senesced cheatgrass, which in fact, if it occurs at high frequency, which those frequencies have been increasing in the Great Basin, if we see that same sort of thing, what you tend to see is this cycle of high frequency fires where the perennial grasses don't have a chance to regrow. And basically you get into this cycle where you're just maintaining cheatgrass, and that's the only plant that you could basically grow under those situations. So that's quite a challenge for a lot of our rangeland, and could be a real problem in the future. Winter wheat is certainly done better with survival, has increased. On the y-axis here I have harvested acres per planted acres. So that's basically the proportion that's surviving to harvest. And in Montana, I sort of had this history of this love-hate relationship with winter wheat for many years, where they would be encouraged because winter wheat would get higher yields, but at the same time, if you had a cold winter, a lot of it would die off, and especially if it wasn't covered by snow. So what we saw is that there are periods where that proportion of harvested acres to planted acres would be quite low. And pre-1985, this was crop killed by low temperatures. Since then, we've had very few of those low temperature conditions, and in fact, so we've seen that winter wheat does much better. So this is a positive, perhaps, for agriculture, but as I said before, it isn't just climate that drives the decision to perhaps plant winter wheat over other crops. There are other things involved. So I can get into that with this graph a little bit, where I show the proportion of total wheat that is actually planted to winter wheat, and what has occurred over time, going clear back to 1915 here, and showing it for each region being a different color in Montana. So the regions that grow most of the winter wheat are the north central, well, the central, north central, and southeast part of the state. So those curves that are all right in here. And basically what we see is generally over time, we saw an increasing proportion of winter wheat. And a lot of that had to do with selecting new varieties that grew well in Montana. And that general trend was more associated with that probably than anything, although it could have been, once we hit this period around 1950, that certainly climate was probably playing some role in increasing the amount of winter wheat that we were seeing relative to other wheat. But then, interestingly enough, even though the climate continued to warm in that period, we actually had a fall off here where gradually the proportion of winter wheat dropped off. Well, again, that's due to a number of economic factors, prices, different kinds of grain policy, trade deals, and things like that all tend to play some role in that. What is interesting, though, is about 1997, we started to see another increase, where we had an increase for almost all regions, where we were seeing this trend of up to about 2014 anyway, of increasing winter wheat, or proportion of total wheat being more winter wheat. Pretty certain that a lot of that is due to the warming winters, and also the productivity, and perhaps some of the patterns in precipitation, even though total precipitation might change, with more fall precipitation to bring up the winter wheat. In other words, winter wheat is planted usually in September, and it needs fall rains to get started and start growing, and yields will be high if you get those rains. Some of those patterns we have seen a switch in terms of the precipitation tending to come with those fall rains, and that's all encouraged winter wheat. At the same time, we also saw rising prices. What's interesting, in 2014, we had a pretty drastic decline, and have had ever since, in wheat prices, and of course the acres of winter wheat start to fall off again. So that's not shown on this graph, but in fact, there's an interaction of factors going on. So it's a little bit hard, again, to tease out what's due to the climate and what's due to other kinds of drivers. Projected changes in freeze-free days, again, using the projections with the 850 parts per million to mid-century. And the greener the map of Montana is here, the more the change in annual frost-free days. And we're seeing that definitely in the western part of the state, looks like good news. We'll have longer growing seasons. So that should increase the diversity of crops that we can grow, species that we haven't been able to grow previously. We could look to places like Utah to see what they can grow, and those are probably going to be accessible to us, or species that could be. So that's an interesting point. Will we be able to grow pineapples? Probably not. But in fact, there will be a diversity of crops. And I think where we're really going to see this is in our market garden production. Those kinds of fruits and vegetables and things that we maybe have only been able to grow with a great deal of risk in the past, we'll see increasingly in the future. So that offers up some potential. In other parts of the state, certainly this longer growing season can bring on some other species. We're seeing a fairly sharp increase since 2010 in the number of acres of corn being produced, for example. Corn was never a species of great production, I guess, in Montana, although I do have a map from 1889 showing that Montana had the highest productivity of corn in that year, and it was interesting. I think it was primarily because we had just a few acres. They were all in river bottom land, and we happened to have a very hot summer that year, and so the productivity for Montana was actually higher than places like Iowa, which was interesting. But that was a per acre productivity, and so in the whole state of Iowa may have been covered by corn. We probably didn't have more than 500 acres of corn in Montana at that point in time. Anyway, in the past few years, we see this increase in corn, partially due to our increase in growing season length. More varieties are available to us, and in Montana, what people tend to do is if they have an outlet for that corn in the form of silage. In other words, if in fact you get a real dry out early in the summer, you don't get the corn maturing to seed, they can cut it and use it for silage, and there is some market for that locally. So in the far eastern part of the state is the place where we're basically seeing this. A lot of it for corn and soybeans, the other crop I'm showing here, which is a common rotation in the Midwest, is of interest because, well, you get paid more for corn per acre. Is that a good thing? That's a big question. Certainly the net returns for those farmers, especially those that have irrigation and can see those crops to finish, it can be encouraging. But again, those are quite expensive crops to grow in terms of just the amount of fertilizer and the amount of inputs that they take to grow is pretty extensive. And so in a way, they make the risk of growing them even greater because you have to put a lot of money into the inputs, and if anything goes wrong, we get an early frost, etc., then you don't get that return, and therefore risk tends to go up with those crops. So it may not be the greatest thing that we would start putting a lot of corn maybe in place of wheat in this state. Productive change in accumulated growing degree days, fairly similar idea here. Increasing the growing degree days means an increase in the growing season, basically. A growing degree day is based on a particular base temperature. Here we're showing it of a base of 0 degrees centigrade. That's freezing. And anything above that, basically, any days where your average temperature is above 0, you start accumulating growing degree days. So that's why these numbers are so high. So you're just adding on the number of degrees above 0 for each day that you're above 0. So that's why the way these accumulations look. Interestingly, in northeast Montana and in central Montana, we see the greatest changes in those growing degree days, and that does open up a lot of possibilities. In fact, northeast Montana has been the region that has been most quickly adapting pulse crops, for example, a wide range of pulse crops. So that offers up some great potential, actually, for diversity in what is basically wheat growing country, but to be able to rotate with pulse crops, primarily these being legumes, offers up a number of things that probably add some durability to those systems, or certainly is an adaptation that could be positive in the face of these changing climates. So species like lentils are becoming very popular. I think we'll see a lot of acres of lentils going in next year. The prices have been very high for lentils, both in conventional and organic production. and that's become quite a popular crop. It can be fairly intensive in terms of some of the inputs. It's not a particularly fast-growing species, and therefore weed control is pretty crucial in it, and that could cause some problems with some of the species there. Austrian winter pea is a great crop, and the possibility, it's called winter pea because it can be planted in the fall. It can also be planted in the spring. But the fact that we have these warming winters, that's a species that's now can be surviving in the winter, and that offers up a good pulse crop alternative that we can put into rotations with wheat. Chickpea is yet another one. Garbanzo beans, another one. So many of these species offer up some nice alternatives and ways that we can create some crop rotations that we think offer up a good way to protect ourselves against some of the risks of crop loss, etc., due to things that will come along with a warming climate. So that's generally a positive aspect, perhaps, of what we're liable to see with climate change. So one of the things I tried to do was to determine choice of crops and what affects the choice of crops by farmers. And here, I combined the North Central and Northeast region, and this is all data out of the National Ag Statistics Service, and Montana has an office there, and we get these statistics each year. And here I have acres planted to lentils as an example, and then what the prior year crop price was received. So dollars per hundredweight is what you see on the x-axis, and this is from the previous year. So wanted to see if how much that crop price was influencing the number of acres being planted. Here we see a positive relationship, which says, yeah, in fact, if the price is high the previous year, farmers are more apt to plant it the next year, or there's more apt to be more acres the next year. Similarly, I can put on the y-axis here previous year precipitation in the region, and sure enough, there's a positive response there too. So farmers thinking, okay, I might have, because it was a wet year the previous year, I might have some stored soil water, which is going to be critical for some of these crops. Then they're apt to plant more of those acres. So these are two factors, two climatic factors, or a climatic factor and a price factor that come together to determine that, in fact, yeah, those two do play some role in terms of whether or not there'll be a decision to plant. So again, the interaction of those factors is crucial in making those decisions. Of course, the other aspect of this, we can't grow crops even if we have a long growing season or have nice high temperatures without water. So precipitation, and the interesting thing about precipitation is that this decadal rate of change in average precipitation shown in this table for the 7 Montana regions from 1950 to 2015 didn't show much, didn't show hardly any trend at all. We see a few negatives and a couple of positives here and there, but not enough to think that there's been much trend so far. Now, with saying that, the climate projection models are indicating some possible increase in precipitation, and maybe some of the slight increase that we've seen in precipitation, particularly in the Northeast and Southeast, has been those places that those are the first regions to widely plant pulse crops, and so maybe this could be part of the reason for that, is that we have seen a bit of an increase in the precipitation in those times. So those historical averages and mean annual precipitation, as I said, trend has been pretty level, or no trend, I guess I should say. But this gives you some sense on this map of just the variation in annual precipitation that we have seen over the last 100 years, and it, as you expect, eastern Montana is drier than western Montana, and so what does that mean? if we look at these models that project out, again, if we look at the 450 parts per million, which, by the way, you know, we're at 400 parts per million. We're probably not far off from this particular projection of change, out to the 850 parts per million. With the increased parts per million of CO2, we should be seeing at least some small regions where we'll get more precipitation, according to the models anyway. So how much confidence do we have? Well, we have a lot more confidence when we see the patterns already. And since we haven't seen the patterns already, we tend to be a little more skeptical about what these mean. And certainly when I talk to agriculturists, people out there on the ground that have to depend on this, I don't put a lot of stock in these particular models just yet. Here's the percent precipitation. That makes it look a little better. And the interesting part about that is you notice that the percent precipitation actually out here in drier, very much the driest portion of the state, might increase. And that could actually open up more areas to even the agriculture that we do now, wheat farming, and even some of these rotations with pulse crops could be encouraged in some of those areas that now can't really support crop production because it's just too dry. And in some of these areas that do support some crop production, but in a crop fallow situation where we only can grow a crop every other year, we have to store water basically 1 year, keep the plants off of the field in order to grow a crop on the other years. So if we do get more precipitation, perhaps we could go to more continuous cropping, which would help reduce soil erosion, etc. So could be a good thing, but still worried about that a little bit. And this is just the percent seasonal change in precipitation. Again, this starts to draw a concern where, oh yeah, well, on a yearly basis, we could see more precipitation according to the models. But they're also saying that, oh, summer, we may not. In fact, we might see a decrease. And that's the period at which those rains could really do us some good in most of agriculture. So not as quite as rosy a picture when you look at it season by season. So if increased precipitation becomes a reality for Montana and mostly comes in the spring, will it improve production agriculture? Well, that's a big question. And like I said, in some ways, if we have longer growing seasons, the people that are really likely, I think, to benefit from this are your market garden kind of production. So we're more apt to see more crops and more production and more potential for CSAs and things like operations like that. However, when it comes to those crops, the irrigated crops and things that need the moisture later in the summer, we just don't, if we're not storing moisture in the form of snow in our mountains, that can be problematic. Okay, so warmer plus wetter plus increased CO2 should increase plant growth. Remember that plants grow, that they're basically fertilized by CO2 in the atmosphere. So those should all come together as a positive thing. Again, it's not quite that simple. So in fact, we need to have precipitation in all portions of the year. Okay, this is another graph that I think exposes something important in Montana. And this, what I did here is on the y-axis is proportional difference between irrigated hay production and non-irrigated production. So think about the fact that a crop that if it gets irrigation, it's going to produce more, but the difference between the irrigated and non-irrigated, we would expect that to just be a constant increase. However, if we look at over time, what has happened, and this combines the effects of precipitation, CO2 increases in the atmosphere, and the warming in the atmosphere. And what we see is the fact that there's an uptrend in each of these regions of the state, more so in the southeast part of Montana where it tends to be drier, is an indication that the difference between irrigated and non-irrigated is increasing. And that difference means that there's a transfer transpirational demand, in other words, the water released by the plant, the sucking of the uh, of the of the water out of the plant from into the atmosphere is increasing, requiring more water to grow hay, especially in hotter, drier parts of the state. Hay is a good indicator because it tends to be both mix of broadleaf, mostly alfalfa, as well as grass. And therefore, it's a good general indicator of, I think, what is happening and why we might not want to count on the fact that wetter, warmer, and more CO2 will turn into more productivity. Because, in fact, it looks like, based on this graph, that in fact the conditions are increasing stress on plants, and therefore the actual outcome is not going to be as positive as you might think initially. Okay, another thing that people are concerned about is significant extreme events, and it's very difficult to get information on extreme events, first of all. And we're hoping, working with NOAA, that over time we'll be able to get more information about what the frequency of these events has been, what exactly, how damaging have they been. Blizzards and livestock is really crucial. And we can see that at times we've had quite devastating effects of blizzards, late season blizzards, spring blizzards in particular. A lot of cows die, and that's indicated in this picture. Those are things that we should know about. If that variation increases, that could be problematic, and it would be good for us to determine if in fact that is happening. Again, the data isn't available to really examine that very effectively at this point in time. What has been examined is crop hail damage, and damaging hails. If we look at areas receiving at least 1 day in 5 years with hailstones greater than 2.5 centimeters, which I guess is an indication that if they're that big, if they're an inch in diameter, they're probably going to cause some damage. We see the higher probabilities are down here in the southeastern part of the state, in Montana, and so this was older work done from the period of 1900 to 1997, and how that might change has not been projected out. Couldn't find any information in the literature, but we can track some of this. I was able to get a hold of number of hail events per year down in this lower left-hand corner graph for just Cascade, Montana, and you can see that, boy, there's some years where it seems to be high, but no real trend in it, unless we start considering from 2010 on. So this might be actually a significant trend because we're looking at like a 4-year period here where there's been a consistent increase. So maybe there's something happening there. We'll certainly keep an eye on that. So extreme events is something to watch for. We'll want to pay attention to that. I don't have a specific graph here, but droughts are also something that we have paid close attention to. We have a great drought prediction network, and there's a lot of effort in predicting drought. I'm not going to go into that here, but keep in mind that there are a number of websites where that is monitored on a monthly basis, and there are projections about where portions of the state are drier than others, and that's particularly useful information. Okay, to kind of summarize some of the key climate change messages, climate trends towards warmer temperature and increased variability will affect crop and livestock production, agricultural practices, and decision-making across the state. There's not much question about that. We're already seeing some of these trends, and we think those will increase. The most tangible specific effects on increasing temperature regime are already evident or likely to continue. The effect on the spring wheat grain fill could be especially important to a lot of acres in Montana. The increase in winter wheat acres, but how that interacts with prices and policy is crucial. Diversified cropping systems, including rotations with pulse crops and innovations in tillage and cover cropping, are allowing and will continue to allow adaptation to climate change, but climate change is only one of several drivers of these agricultural innovations. Climate change affects commodity agriculture different than it affects non-commodity agriculture. So certainly we have We have the market gardens, as I've said. There are probably positive things out there, although a lot of those gardens rely really heavily on irrigation. And if we have late season loss of irrigation, their seasons are going to end up being shortened. They might be lengthened in the beginning of the season, but shortened toward the end. So can be different effects there. Every component of agriculture, from prices to plant pollinators, crop and livestock pests, exhibit complex relationships to climate, depending on the location, weather variability, and agricultural practices. And economics and policy will almost always play some role. So in terms of creating adaptations and creating strategies for adaptation, it becomes complex and highly important how we treat and understand the interactions among the different factors driving those. So, and I just simply show that with this diagram, kind of trying to get some sense for an agricultural decision is based on expected price received for a crop or livestock, and that plays a large role in how decisions have been made in the recent past, and certainly currently. Government policies play a large role in that. Pests play maybe less of a role and are kind of always there, so they've always managed around it. Just like climate, as I said before, climate's always been variable. So do you do something different because of climate? Well, that's probably increasingly, we expect that climate to play an increasing role in how decisions are made. Certainly production inputs are something important to consider, and how do farmers make a wise decision to maximize a net return with regard to production inputs. So production inputs tend to be used as insurance that you will get a yield, and they've always helped suppress the variation that comes from all of these variables. But as you add variation, particularly in one arena, that just intensifies the effects of risk in the system, and therefore we need to look to some of these other aspects and how they play a role in decision to determining how we might influence those decisions in the future, or might need to influence those decisions in the future. And thinking more about how do we maximize wise decisions or how do we make wise decisions to maximize resilience in our system is probably a better way to look at it than simply year-to-year maximum net returns. So I like to think of our system, our production, our net return on the y-axis here over time, and the ball might be our system here, and it's sitting here on this plateau. But what we need to do is have farmers be able to recognize, farmers and ranchers, be able to recognize where they are, where their system resides here, because we don't want that production and net return to fall off this edge so it cannot climb back up onto this plateau. So being how close you are to this edge is really important to know. And we think that the climate could actually push you over this edge if we're not paying attention. So playing a role in how we manage pushing this ball back onto this plateau so we're as far from that precipice as possible, making our system more resilient will be the crucial aspect of what we do here. Just to give some sense of what's the relative amount of uncertainty and variables driving dryland wheat net returns as an example. Here I've plotted the Palmer Z index, which is just think of that as that's the drought index, and basically if we think of that as being a climate variable relative to the cost of nitrogen fertilizer, relative to the price received for wheat, and then of course totaling those, we can kind of get a sense for what is the relative variability. The coefficient of variation is simply looking at the variance relative to the mean, and it moves along as every 5 years, or every year it's updated on a 5-year average. So if we use that, we say, well, gee, the drought index, or the climate variable here, tends to be the one that has the most uncertainty in it relative to cost of nitrogen and price of wheat. And therefore, we should anticipate that any increase in that is going to make our systems even more uncertain and potentially less resilient. So we have to keep in mind those things. So we have variability in input costs, variability in prices received, and so what does that mean? And can we simply use inputs like fertilizers to increase the resilience of our system, which has been the pattern in much of our at least crop production.
Sorry, I'm cutting in. Hey, Bruce.
We need to ask that question.
I just want to let you know we have about 4 more minutes.
I'm just about.
Awesome. Great.
Right, and then this is my last slide, basically.
Okay.
In fact, I'll just go to this. Just wanted to recognize that this is part of the Montana Climate Assessment headed up by Kathy Whitlock, and the other sector heads are listed here. And thank you for your attention.
Okay, Bruce, thank you so much.
That's all I have.
That's a lot of great information. And it looks like maybe Jane is about to ask a question. If anyone else has questions for Bruce, please go ahead and type them in, and we can do a few minutes of question and answer. Carolyn says thank you. You got that one, Bruce?
So Jane asks, will the chapter of on agriculture have data information on plant diseases and insects? It seems like they would, prosper in warmer, possibly wetter conditions. Absolutely, and we have lots of detail. Actually, I pretty much glossed over that, but in the interest of time. But yes, there will be a fair amount of detail, at least on the disease end. The insect side, there's a lot of things can come into that. A lot known about insects, and predictions could be made. We draw on primarily the example of the weed stem sawfly as the complex interactions that might occur with warming and increased precipitation and those kinds of things. So yes is the answer, Jane.
All right, does anyone else out there have questions? You start typing, I'll be able to see them. All right. If you do find that you have questions, if you walk away and you realize, gosh, I wish I had asked this or that, feel free to contact myself. It's anna.tuttle, and then the number 1, anna.tuttle1@montana.edu, and then get your questions to Bruce or to other people who might know the answer. And Bruce, thank you so much. I appreciate you taking the time. And to all of you participating, thank you. Just a quick reminder that next week is our last webinar. Again, it's Ashley Ballantyne who'll be discussing the forests chapter of the state climate assessment. Same time, same place. Hopefully we'll see you then.